All right, here we are for another biology video. So in the last video, we were talking about fossils. And before that, we were doing the communalcule activity, which had to do with fossils. And one of the most important aspects of fossils, other than what they looked like, are the ages of the fossils, right? And so we've been doing this stuff for about a week now. And it's now time to talk about how do we know how old a rock is, right? Um, on the screen, you have a bunch of sedimentary rock. It's a bunch of layers of rock, right? And these are the types of rocks that you find fossils in a lot because they usually form underwater, and then geology happens and the water goes away, and the rocks are exposed, and then you can see all the fossils inside there, right? Now, one of the basic ideas is that the layers that lower down are older than the rocks at the top because it has to go, the layer gets formed and then another layer on top of it, right? So you can tell the relative ages of things fairly easily just by looking at, is it at the top or is that the bottom or the middle or way down here? But if we want to know the actual date, we need to use something called radiometric dating, right? And so, how do you determine the age of a rock? You use radiation. Radiation is what happens when certain atoms break down. They are unstable and they're going to release energy in particles and they're going to decay, is what it's called. This happens at a known predictable rate. So it's happening right now and it'll continue happening at the same basic rate that it's always been happening. And so, if you can measure how much radiation is remaining, how many atoms of radiation are remaining, then you can figure out how long it has been releasing energy in particles. The rock has been releasing particles, right? And so this might seem sort of complicated. However, we're already familiar with this basic idea with an hourglass, right? The hourglass has the sand at the top and they fall down due to gravity. It's not radiation, it's gravity. They fall down at a known predictable rate. And so if you measure how much sand is remaining at the top, you can figure out how long has gone by, right? And so this is an hourglass. And when all the sand goes down, it's 1 hour. But you'll notice that there's these little lines, like right here is a line that says 60 minutes, and then there's a 30 minutes. And this one you can't really see, but it says 15 minutes, right? And so by measuring how much sand is left in the top, you can figure out how long the sand has been dropping. And so that's the same thing we're going to do with the radiation in the rocks. The rock has a bunch of atoms that are radioactive in it. We come by and measure how many atoms are left, and then we can see how old they are. So first, real quick, we need to talk about atoms. I don't know how much you know about atoms, but atoms consist of three basic parts: protons, neutrons, and electrons. The protons are the positively charged things inside the nucleus. The electrons spin around really fast. They are electrically charged. And then you have these neutrons that are neutral in the nucleus. They don't have a whole lot to do with what we're going to talk about today. Now, this atom is a carbon atom. It has 6 protons and 6 neutrons. This atom that just showed up has 8 protons and 8 electrons. Sorry, I said it says neutrons. It also has 6 electrons over here. This one has 8 protons and 8 electrons, and that's oxygen. And this one has 92 protons and 92 electrons, and this one's called uranium. Of course, all of these are found on the periodic table. The number in each of these tells you how many protons and therefore probably how many electrons it has. It's a little more complicated than that. When you get into chemistry class, it might make a little bit more sense. But in any case, the point is that there's all these different elements and they're based off of how many protons that they have. And so the neutrons are a little bit weird. Again, we don't really need to talk about neutrons too much, but they're in there to kind of balance out what's going on inside of the nucleus. So here's where one little thing before we get into radiation, you're going to see some numbers that are associated with these different elements. Like, for example, this one's called carbon-12, and this one's called carbon-13, and this one's called carbon-14. These are called isotopes. Isotopes are different versions of the same element. They have usually different neutrons, as you can see, like right down here. They all have 6 protons, which is why they're all carbon, but they have different neutrons. Again, this isn't a huge deal for us, but just know that when you see these numbers that come at the end after the name of the element, it's talking about a certain version of that element, and that's really all you need to know about right now until you get to chemistry class. Here's oxygen. As you can see, there's different isotopes of oxygen out there as well. There's isotopes of lots of different atoms. Now, radiation, radioactive decay. Like I said, certain atoms are unstable, and they're going to release energy in particles as they break down. So here's a general idea of what's going to happen. You have your thing called the parent isotope, the parent atom, and it's going to go through radioactive decay. There's 3 options of what it's going to do. The first is it's going to spit out something called an alpha particle, which is actually 2 protons and 2 neutrons. It's actually like if you think of like little particles in the nucleus, they just shoot out. That's called an alpha particle. And notice that when that happens, the parent isotope turns into the daughter isotope that's a little bit different than it was before. We'll get back to that. There's something called a beta particle, which is an electron. Basically, a neutron shoots out part of itself, the negative part of itself, and that's called a beta particle. And then there is something called a gamma ray, which is a photon, high energy photon. This one's a little bit different than the others. I forgot to mention that this one does look a little bit different than the parent. One of the blue has turned into a yellow because it lost its electron, so it changed from a neutron into a proton. That doesn't really matter. But the daughter isotope here doesn't change because photons are kind of like light, and so that doesn't make the element change. Anyway, this is how radiation works. Why do you care? Alpha particles are not that strong. A piece of paper could block an alpha particle. A beta particle is a little bit more energetic, can go through regular paper, but something as thin as a small piece of aluminum can block a beta particle. So like a tin can armor would block beta particles. Gamma rays are the ones that you don't want to deal with. Those are the ones that are going to really destroy your cells. They are not going to turn you into the Hulk. They're just going to basically kind of melt you from the inside, kind of thing. Most of the rocks that we're going to talk about don't have anything to do with gamma rays. Sometimes you're going to see alpha and beta particles as we go along, right? Now, again, one thing that I wanted to point out is that when they decay, they become different elements or different isotopes. Carbon-14, which is this one, is going to turn into nitrogen-14 when it loses an electron. And you don't really need to know how exactly it happens again, but it changes itself. Radium-226 decays into radon-222 when it loses an alpha particle. The one we're going to talk about mostly is uranium. Now, this one's pretty crazy, as you can see. Uranium-238 eventually leads to lead-206, but there's all these little tiny steps that happen in between it. This is all a bunch of chemistry and physics that is well beyond what we need to know. What you need to know is that there are certain elements that have certain versions called isotopes, that they are unstable, they release particles, and they change into something new. And we can measure all that happening, and this is going to help us to figure out the age of the rocks. So there's the rate that the rate that the radiation happens is predictable, but it's a little bit more complicated than just how much is left. There's something called a half-life. It means how long it takes for half of the atoms to release their radiation. Radiation is a very random process. We don't know exactly which atom is going to decay and when it's going to decay. But when you take the big group of atoms, on average, half of them will decay at a pretty reasonable rate. It's a weird way to measure things. We measure it in how long it takes for half of it to disappear. You'll kind of see what that means in a second when I show you a graph. But I want to show you first that there's a bunch of different types of radioactive elements, and they have different half-lives. Some of them relatively short. I know 5,000 years doesn't seem too short, but it's pretty short as far as like the history of the Earth is concerned. Some of these things, like this one, is about the same age as the Earth, 4.5 billion years old. This one is older than or longer than the age of the universe. So for rubidium to turn into strontium, half of it hasn't even disappeared yet, because it would take close to 50 billion years for half of it to go away. The way they measure this, again, is way beyond what we need to know. It has a lot to do with physics and chemistry, but we can measure the rocks and how fast the radiation is coming out of them, and then they base that to make these different half-life measurements. So because it's half-life, you get a weird looking graph like this, right? It's not like it's not a linear graph where you slowly lose the same amount until you finally get down to zero. Because it goes by half, the amount of half is a relative percentage. And so at first, half means 50%. I mean, it is 50%, but again, let's do it with the atoms. You start with 20 atoms that are radioactive, none of them that are non-radioactive. After one half-life, 50% is going to be left, which means that 10 of the atoms have gone from being radioactive to non-radioactive, right? 10 of them have decayed. Now that's 10 right there. Now the second half-life that happens during this section is also going to remove 50%, but 50% is now 5, right? Because half of 10 is 5. And then, of course, we're over here and we're down to 25%. But the percentages are getting smaller as you go along. 5 is then going to decay by 2.5. And I know you can't have half of an atom, but again, this is an average. So this makes instead of a linear graph, you get this parabola kind of thing, where it's going to level off and get more and more flat as you go along. We'll come back to that, right? But we can use this graph to figure out how old rocks are. And I've already kind of been showing you how you do it by drawing lines on the graph. So let's do an example. Let's say we find a rock. We want to first measure the percentage of radioactive atoms, right? So again, this is the part where you would send it, if you were a biologist, you would send this to a lab, and then they would go and they would run these tests on it, right? Let's say that they come back and they tell you there's 40% is remaining, 40% of the radiation. Now over here, notice on your graph, there's an axis that says proportion, which again, that means percentage of parent atoms remaining, right? So that's the amount of radiation still in there. And so we want to go over to 40%, and we want to draw a line going across, right? Because that's the 40% level. We have that much left. We draw it over until it hits the curve, it hits the purple line. Then we draw a line going down, because that's going to be where it intersects the time axis. Now, and again, time here, it's time 1. There's no such like time 1. Is that seconds? Is it minutes? Is it hours? It's none of those. It's half-lives. So it's somewhere between 1 and 2 half-lives. This is the thing about graphs, that not every single number is shown on the graph. They all exist on the graph, but they're not all labeled. I would say that about halfway is right here, right? So like that's about 1.5. But the line, this one is a little bit less than 1.5. So I'm going to say that's about 1.4. This rock has lived 1.4 half-lives. And I know rocks aren't alive, but it has been 1.4 half-lives since this rock was formed. But how long is a half-life? This is where we have to do a little more math, because it depends on which element we're talking about, right? They all have different half-lives. So the graph that you're seeing here, and the graph that you're going to use on an assignment coming up in a second here, they always look pretty much like, this graph looks. The times are always in half-lives, but then you will eventually have to fix that to make it into years, right? And so I'm going to show you how to do that. Let's say that this rock isn't a rock. It's actually like a piece of wood. It has carbon-14. Carbon, of course, is for living things. When living things turn into fossils, they turn into rocks and all the carbon goes away. So carbon dating is only for things that are carbon-based, usually old samples of wood or something like that. Maybe if you found a bone that hasn't actually fossilized, it's just an old bone that's just been sitting there for a long time and all dried out, you would use carbon. Now carbon-14 has a half-life of 5,730 years, right? And so how many half-lives is that? I want to then multiply that by the number of half-lives that it's been. And that will then tell me the number of years. 5,730 times 1.4 is 8,022, right? And so if this was a bone that was found that had 1.4 half-lives that had gone by, then this is going to be an 8,000-year-old bone. But what if this was actually a rock that was made out of uranium or had uranium in it? Uranium has a much different half-life, 4.47 billion. But again, the rock, the measurement over here just tells you how many half-lives. So we're going with that same half-life of 1.4 half-lives. Now would become 6.3 billion years, right? So the table is the same all the time. The math is actually going to be the same pretty much all the time. What changes is which half-life you are using, right? So you use the graph to figure out this number, and then you multiply by the number that we already know, right? So let's do an example, right? On a scratch piece of paper right now, you can do this problem. We have a sample of rock that is measured to show that it has 25% of its uranium left. How old is this rock? And then I wasn't sure if you'll be able to see this number over here, so I reminded you that the half-life of uranium is 235 is 704 million years. So how would we go about doing this? Well, first step is to measure the amount of radioactive atoms. We know that it's 25%, right? Instead of 40, we're at 25. Then we're going to go from that spot to the y-axis. So 25 is around right here, and I'm going to draw it across, right? And then I'm going to draw it down, and it goes to the 2, right? So that means 2 half-lives have gone by. So then this is uranium. I want to take 4.47 billion times 2, which is, of course, times 2 is 8.94 billion years. This is a very old rock, right? But in any case, that's how you do it, right? You look at the percentages, you use the graph to figure out the half-lives, and then you do that quick math problem, right? So there's something interesting that happens because of the half-life thing, which is that technically, if you keep dividing things in half, like you never actually get to 0. So when you get way down here on the graph, it's not letting me draw. There we go. When you get way down here on the graph, the line gets too level. Like it doesn't, you can't really tell the difference between where the line is because it's starting to level off too much, right? So you need to choose an appropriate isotope. If you're measuring a rock, and it has carbon-14 in it somehow, and it also has uranium-235 in it somehow. If it's an old rock, you want to make sure that you use the uranium. You don't want to use the carbon-14 because it will run out, basically. If the atom has a short half-life, then after 5 half-lives, basically, you won't have enough left. I know it says 7 on here, but pretty soon you get to such little amounts that you can't tell. But somewhere between 5 and 7 half-lives. There's so few radioactive atoms that you can't detect it, right? So again, carbon-14 has a half-life of 5,730 years. After 5 half-lives, that's approximately 35,000 years. But 5 half-lives for uranium-235 is like 40,000 years, maybe closer. 400, no, I'm just going to do my math. Instead of trying to do my math in my head suddenly that I can't do, 704 million times 5 is 3,520,000,000. That's a long time, right? So again, the half-life thing always stays the same, but it's the years that are different based on the isotope. So you don't want to use carbon for something that's super, super old. But you also don't want to use uranium for something that you don't think is that old, right? Because the opposite thing happens over here, that where, like, let's say you measure it and it's only been like 0.1 half-life, then that's still kind of the same thing as when the graph is too flat on the end. It's too flat over here and you can't measure enough accurately. In any case, the point is that you have to choose something that hopefully is within this kind of range of the graph. And as you saw on here, I wanted to show like the idea of like the, what do you call it, hourglasses again, although these ones aren't hourglasses, right? They're minute glasses. And so let's say I'm using the 4-minute glass, right? And I'm measuring my, I'm doing something, right? I'm doing my homework. And so I start my 4-minute timer and I'm doing my work and I'm doing my work. And then I look back and when I'm done, I look back and I see, oh, the 4-minute timer, this has gone down. Like all the sand is gone. It must have only taken me 4 minutes to do my work, right? And like, of course, that doesn't make sense that the timer ran out before you finished. And so there was all that time that you weren't able to like account for. That's what I'm talking about over here with these half-lives, in case I wasn't clear before, which is why I have these analogies, right? If you use something that has too short of a half-life, all the radiation will go away. And so it'll tell you, oh, this thing's only 35,000 years old. But actually, it's way older than that. But the radiation ran out long before you were able to measure that kind of thing, right? So you want to use the appropriate isotope, the appropriate half-life on here, right? And so again, I was just trying to show that there's different hourglasses, and then there's different isotopes. So here's where you would go and now do this half-life simulation lab. If we were in class, you would actually do this with pennies, basically. So here's some background in case you wanted to read it again. We probably won't talk about relative dating until a different video. But in the procedure, what you would have done is you would have had 100 pennies. I would have given you 100 pennies. And you have a cup. You would shake it all up. And those would be your atoms, right? The cup would be your rock, and the atoms would be the pennies. And you would shake it, and then you would dump it all out on your table. And then you would look, and you would take all the ones that are tails, that ended up tails up, and you would get rid of those. You'd put those off to the side. Those would be the ones that have already lost their radiation. You would then have a certain number left, and you would record that number in this data table. And then you would take those heads, the ones that were heads, and put them back in the cup, not the tails ones, right? So you would have only some of them left. A bunch of them would now not be in the cup. You would shake the cup, you would dump it out again, and you would do the same thing. You'd remove the tails, you would count the heads and put them in the table, then take the remaining ones and put them back in the cup, and keep doing this, right? Now, I'm not going to have you do that. Maybe you have 100 pennies. So I don't want to have to deal with all that. So I'm just going to give you the data, right? This is a sample data that came from a lab from last year. It shows the remaining heads at each round, right? So like you had at the beginning of round one, there was 100 remaining. And then in round two, there's 54 remaining. And then in round three, there's 27 remaining, and so forth. You need to graph that so you can make a half-life graph. This is practice to do the labels, right? So make sure you have all your labels and everything correct. And then there are a few questions where you have to use the graph to answer these questions, right? So let me know if you have any questions at the end of the video, or come to office hours and we can talk about it.